Okay, hi and welcome to video notes on linear regressions. Now, you may ask yourself, what does the word regression mean? We'll get to that fully in just a minute here. But before we do that, let's just kind of say what it is it's going to help us make a function for some data that we collect in real life. Not the stuff we've been using all school year. That's perfect data. It means it works exactly like the line of the function. It fits right on there, or it makes the line of the function. But we're talking about data that we're going to find out in the real world, stuff that we're going to collect. It's going to be messy. It's going to be not exact. It's going to be all over the place. So this technology, or using technology to help us with regression, makes a model for a whole bunch of random data, or not random data, that will put a math function right on top of it. And that's really what regression's about, taking real world data and taking a function that we're very familiar with and putting it down for us so that we can use it to speculate or guess what's going to happen next. And this is really how most stuff in the world works. So let's talk about that. Let's say I had a question, something that I was wondering or pondering about. Just the other day, one popped up to me. I took the car in for an oil change, and I'm like, hey, I get this oil changed, and they say that it's good for my car, and I know that it'll probably burn up the engine if I don't, but do I need to get it every 3,000 miles? Do I need to get it every 6,000 miles? Can I get it once a year? What about once on the time of a lease if I had a lease car? How does that affect it? And how much money will I have to pay, more importantly, if I don't? What happens if something breaks? Is that cheaper than not getting the oil changes? Now, I don't know if that's linear yet, but let's pretend that I did a form and I collected some data on that. But Let's go ahead and kind of pose what would happen in this whole sequence here, and we'll talk a little bit about regression and doing it. So do oil changes really matter? Well, I don't know. I just said I'm going to collect some data. But after I collect the data, what do I do with this data? Do I just look at it and say, oh, he paid this much, she paid that much, this is how much total that they had to pay? Maybe, but that's probably not the most efficient way. What I'd like to do is take that data and plot it. Now, the reason I want to plot it so that I can see it with my eyeballs, right? And then I'm going to get an idea of maybe it fits one of the functions that we've been talking about all year. Maybe it's a linear function. Maybe it's quadratic. Maybe it's exponential. I don't know, but each one has its own unique characteristics. And if I can figure out if a model goes with that data, well, then maybe I can make some guesses about should I get my oil changed or not. So how do I do that? Well, now that I've plotted, what do I got to do? Well, I got to make a model. And we did that by hand in the previous notes, but this is going to be real data. It's going to be kind of messy and all over the place, and it won't be as nice to do by hand. So that's where I would use regression. Okay, so I'm going to take this calculator, and I can do regression by hand, but it's a long process, and we want to shorten it up for this class. So I'm going to take the calculator or whatever technology I'm using. I'm going to have it make the model for me. Now, my only job then is to decide, is that a good model? Does it fit what it's showing there? Is it really look like a linear function is going to model that, or a quadratic or exponential? And then better yet, what does it mean? How can I use it? That's what we're going to do with regression. So let's take a look at that. Well, let's answer some of these questions. So let's talk about regression first. So let's define regression a little bit better. Regression then is to calculate a model of some data with a linear function. We're going to talk specifically linear regressions right now, of course. We'll do the other regression types when we get to class. So we're going to talk about linear functions, assuming that it's a linear function, but not all functions are linear, just like I said, or some functions don't even have a relationship. And so once we make a model or use technology to aid in that process, how do we tell if it's a good model? That was one of our other questions there. Well, we can get also a calculation by doing regression, what we call correlation coefficient, which is some decimal that will tell us how good the model is. That's what we're going to do today in class. So let's take a look then. I got some data here that was provided for me on oil changes. And so let's say that this here is the number of oil changes per year that these people got. And we're going to use this as an average. So we'll say on the average of the lifespan of the car that they owned, they got roughly 3 oil changes per year. Because we know that if you have a brand new lease and you get your oil changes per year that are recommended, you probably don't have anything that you have to fix or even take in to have fixed. So not in the first year will it matter, but over the life of the car. So these would be how many oil changes on average they got per year. Okay, over the life of the car. And then here's the total cost of repairs, because as we said, maybe the first year you don't have any repairs, maybe the second year you don't have any repairs, but maybe the 3rd through 10th year you've got lots of repairs. So this will be the average cost over those years, even though some years you may not pay, you may pay a lot later on, so we're going to average that. So this is the average oil changes per year, and this is the average cost per year. So that's the data I collected. What we would do then is we'd put it on a graph. And you can see that here. You can see the money values plotted on a graph, right? Number of oil changes being the independent variable, and the cost for the engine being the dependent variable. So having that, we plotted it. You can see all these money things on there. Well, that's where we'd go and grab technology, and technology then, by doing a regression, a linear regression right now is what we're focusing on, would draw the line that would fit in those the best to represent it. And if you look at the plots, that looks very much like a line. It doesn't look quadratic. They don't go up over here, or they don't take a really steep curve and look exponential in any fashion. That doesn't even look exponential or curve. It doesn't curve up as we go to the left here either. So this is definitely what I would say is a linear function, okay? And we can model that. And you're like, great, does that mean then by your model that if I have 8 oil changes per year that I'll pay nothing? No, that's not the reality. We can see that there's sometimes that maybe you won't pay anything over the life of the car. Maybe that was just the best car ever made. But realistically, these don't all fit on the line. Some of them are on the line, some of them are off the line. This is an average. Like the most common event would be from here. So that means that this value could work farther out here, but you would never pay less. Nobody's going to pay you not to get, when you get too many oil changes. So it only fits to the data, but this is a linear function, linear data. Here's another one let's look at quickly. Here's some data we've got about weights of a motorcycle versus height that it can jump in inches. And you can see here that this data is linear. And if we did a regression, there would be the line of regression, the model that we'd want to use to provide that. So some motorcycle company may say, hey, if I can make my motorcycle 17 pounds, dirt bike, if I can make my little dirt bike here, my pedal bike, if I can make that 17 pounds, how high could this people jump that are doing these jumps, that are competing in these competitions? We could guess about how high that would be. So a company may use something like that because this is linear. So we could project out and say, well, if I could get down to this weight, then I could say, hey, I can jump over 12 feet or 11 feet with this bike. You could possibly jump that high, and that may get you more buyers. So there's lots of applications to having a model put down on top of real data, so that you can make some guesses where you haven't been able to test. And is it worth going out there? Or is it worth getting an oil change? Or is it worth not getting an oil change? Can I fit somewhere in here and get a couple oil changes and pay a little bit of money on maintenance and spend less on oil changes and make the most out? Is that possible? With the regression, you can find that out. Both of these, by the way, before we move on, have a strong regression, meaning that all of these points are almost on this line. And that's what we're going to talk about is correlation coefficient. That's going to tell us how good our model is. One of our other questions that we have to answer. Okay, let's go over to the notes here and see if we can fill some stuff in. So over here then, here are some basics for regressions, specifically linear regressions. So linear regression analyzes the relationship between two variables, an x variable, an independent variable, and a y variable, a dependent variable. It's important to remember that, independent and dependent. Okay. The correlation coefficient is what we talked about last there. That's that R value. And that R value tells you how strong, the strength of the relationship, also which way it's trending. And trend's a word that you want to probably write down. Trend means the way the points are flowing or the cloud of points are going. So if we were to look at this is trending up from left to right. So is this. These would be trending down. And we don't want to say that they're going down because that would mean something different. We want to say that they're trending down, that all of the points are moving moving down the y values or trending down. Okay. If you find that this correlation coefficient, which is a value that'll come up from doing the regression that'll give you R, if it's a positive, well, first let's say this correlation coefficient is a decimal, right? And it's a decimal, and you can see that I get that a little bit down here. It's a decimal between 0 and 1. Oops, I probably should move the 0 in the middle here. A decimal between 0 to 1 to -1. Okay. The closer it is to 0, the weaker the relationship is. Okay, and I think I go through that. Let's highlight that so we can see it right here. All right, the weaker the relationship is. The closer it is to the 1 or -1 values implies that it's a stronger relationship. And if it's exactly 1 or -1, then it's a perfect relationship. If the value is on that negative decimal side, that means that the relationship is going to trend down, meaning that you will have a negative slope for your model. And if it's positive, it will trend up. So that means that if the decimal is close to 1, that means that your trend or your slope of your line of best fit or your regression model will trend upwards. Okay, so you can see that I put the r's here. This is close to r +1. This one's close to an r -1. This one's going down. This one's going up. These points are farther away from our line, so that it's going to be closer to the 0. It might not be 0. It might be like 0.3 or 0.2 or -0.18 or -0.4. Those would be values that you would see, but that would say that it's a weaker relationship, meaning that there's something there, but it's not I wouldn't sell my house and bet on it, okay? Over here, you may want to bet on these because that's trending pretty strong. All right, we'll do these TI-84 instructions on how to calculate the line of regression on your TI-84 calculator in class tomorrow. But for today, we're going to use Desmos to talk about that. So we're going to take the example here and run through this with Desmos. Okay, so our example then, if we read it here, it says the table shows time spent by 9 students working on a community service project and the amount of money that they raised. So what we've gathered here is the hours that these students have worked, right, over the community service project, or each student here that's collected, this is how many hours that they worked, and this is how much money that individual student raised. Is there a relationship, first of all? Well, we don't know. We've checked 2 things that could have a relationship. In our minds, we probably suspect it has a relationship. We can probably even make a hypothesis. So pause and write down what you think is the relationship, how many hours, how much money you get. You can look at the data and speculate. So why don't you do that? But here's what we would do next. So pause. And then next, what we would do is we'd take this data then, and we'd plot it. We don't know that it's linear. Well, we do because that's the section we're in. But let's pretend we don't know that. Then we'd plot the data. This is where we're going to use Desmos and its abilities. So I'm going to pop open Desmos. So here's Desmos. Here's the same values for those. So here's the students, the hours that they've put into driving up money for the charity, and then here's the money that they've collected. So I've plotted them, or had Desmos plot them, and it looks like this. Just looking at that data, I want to say it looks very much like I could draw a line right through the middle of them. It doesn't look quadratic. It doesn't look like it's curving up. It doesn't look like it's curving down. Maybe a hint that it's curving down. Maybe a quadratic model would work here. I don't know, but I feel more linear. It definitely doesn't look exponential in any fashion. Exponentials will have a very sharp curve, so not exponential. But this is not perfect data. This is real data. You'll notice that they're not all in a line, or they're on a quadratic or on a exponential shape. So now what we would do, we say, Desmos, please go ahead and make me a regression, which means make a model for this, and then tell me how good that model fits these points. So to do it in Desmos, you would type you type in whatever function type you were looking for. So for this one, I believe it's linear. So I wrote something that looked very similar to y = mx + b. Using the little squiggle here tells Desmos to make it a regression. So if you're doing this at home, make sure that you use that little squiggle. Additionally, when you make your table, notice this is called x1 and y1, not just x and y. So when you type in here for your model, instead of typing y = mx + b, you'll type y1 squiggle equals or squiggle mx1 + b. And what it'll do when you turn it on is it will make the line that fits that data the best according to its regression algorithm. Okay, and it says this is the model. So if you look at this, this is a line that goes on forever up here to positive infinity and goes down here to negative infinity on the y-axis and the x-axis and both sides, right? Negative infinity, positive infinity, back and forth. This is the line that best fits. Of course, there's no value to this. This function doesn't exist or mean anything outside of quadrant 1. So we're going to cut it off, right? That's the reality of the situation. The function goes forever, but reality stays in quadrant 1 because nobody's going to take away money because you don't rate or go out and fundraise for this event, right? And they're not going to pay you negative monies or take negative hours. It doesn't make any sense. So quadrant 1's where the function exists, but it does go on forever. I want you to understand you put a function that works everywhere for a certain application that you need to end by your choice, what makes sense. So looking at this, we can get a couple of things here. One, you'll get your function. They tell us what the slope is, right? It's 15.24, and they tell us what the y-intercept is $34. And we may need both of those actually to answer some of the questions. We'll need a little bit of that. Additionally, what it'll give us is this R value, and that's the value that we were looking for. This tells us how strong the model is, how close these points are to the line. And the closer to 1 or -1 that it is, the better. And if you look here, we've got positive 0.95. That means it's really close to 1, and it's positive. It's trending up, which means positive slope, positive R value, and it's really close. So this is a really good model. So let's go back and write this down and use some of this information to answer the rest of the questions. Okay, so here's the first question. What is the slope of your equation? Well, there it is, 15.25. What does it mean in context of the problem? Well, it means that the students are raising roughly $15 an hour. And if you look at this one, though, $15 an hour, that means 15 and a half, right? So you're at like around 20 some bucks, right? It says 50. But don't forget, on the next question, it says, hey, what is the intercept of your equation, your y-intercept? It was $34. And what does that mean to the context of the problem? Well, that means that we started with $34.58 in our bank account. So maybe there was some previous money, but they are earning $15 an hour after that initial $34.58 that's in there. So these table values don't make sense exactly to $15.25 an hour, but they do when you understand how much money was originally in the account. And that's very viable. Okay, what is the correlation coefficient for your data, and what does it imply about the linear relationship? Well, it was 0.95. It means that it was positive, so the values are trending positively or trending up, which means I have a positive slope, and it's a very strong relationship. So we did graph the regression. We already did that. We saw that on there, and we'll do that again in the 84 tomorrow in class. How well does the line best fit? The line fit your data, sorry about that. How far are the points far away from the line? No, it fits very well, and the points were very close to the line. There were some above and some below, and that's exactly what you want to see. So, is there a strong positive linear relationship between the number of hours worked and the money raised? Yeah, of course. It did look like there was a relationship there, and our R says that there was. Do you think the number of hours a student works causes them to raise more money? Yeah. What other factors might be involved? Because there's always more than just two factors in anything in the real world, right? It's very hard to get down to just two factors. What other factors may apply? Well, you can pause and add your own, but I've given you a couple. And the big one, I think, is just the awareness. The more that there's students out there trying to raise money for some event, the more people are going to know about it, the more people are going to talk about it, and the more people may give money. So, and that would fall under the same thing as some type of advertising. What else are they putting out there? Flyers and pamphlets, so that when these kids come around, there's a lot of people ready to give money. So lots of other contributing factors you can apply on your own here. And that's always something to consider every time you talk about these. What other factors may apply? Maybe it's not just these two. All right, so that's today for the notes. Thanks for watching. But just remember, regression is taking a model, a math model, right? Y equals mx plus b in this case, and putting it on data that looks random or has a small trend or a strong trend, right? And seeing how that model can help us decide what to do or what questions we can answer. All right, thanks for watching. We'll see you in class.